An important periodic trend that is important later on in the course, especially when we talk about Lewis structures, is electronegativity, EN. Some textbooks also call it electron affinity. We're going to define electronegativity as the ability of an element to sort of attract electrons. So like in an electron sink, some elements are naturally have a gravitation, a tendency towards really being attracted to electrons, more so than other elements in the periodic table. To be frank, most of the elements here like to give away electrons, so they're not really electronegative. Well, whereas most of the elements here like to take electrons. They like to grab electrons, have a larger electron affinity, and obviously the noble gases have a full shell of electrons, so they're inert and they're noble. So electron configuration has the periodic trend where it's going to increase from left to right across a period in the periodic table. So here is an increase, and then as you go down the periodic table, as you go up in the periodic table, and as you go up a group in the periodic table, the electronegativity is going to increase, or electron affinity is going to increase. So once again, to repeat our trend, the electronegativity or the electron affinity, the ability of an element to pick up, grab, be attracted towards electrons, increases from left to right in the periodic table, and it increases down to up in the periodic table. So let's give you a general idea. Mostly let's focus here in the periodic table, your halogens, your oxygen, your nitrogen, your fluorine, obviously all the halogens, your phosphorus, and these are generally going to be the elements that are going to really pick up electrons and be attracted for them. So let me give you an example of this idea of electronegativity. To do that, I'm going to draw the structure of a molecule known as formaldehyde. So formaldehyde will have, as part of its covalent structure, remember, nonmetal, 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 nonmetal. So really it's all covalent bonds, it's sharing. So what I want to convince you, and this is the whole idea behind electronegativity, is that this carbon-oxygen double bond is not a 50-50 double bond. It's not shared equally. The oxygen actually picks up, I'll draw this in green, the oxygen actually has more of an attraction towards these electrons of the double bond than carbon. So the pulling power of this oxygen, the fluorine, the halogens, the oxygen, the nitrogen, the pulling power towards the electron density of this double bond is much greater for the oxygen. And what happens is that this oxygen, by pulling, think of a vacuum cleaner, pulling, or like a tug of war, the oxygen is winning in this bond in terms of tugging and pulling the electron density towards itself. And that is what electronegativity is about. So really what we say is that this part of the molecule towards the oxygen side is partial negative. This is called delta, so we'll call it partial negative, making this partial positive at the carbon end. So within this molecule known as formaldehyde, you have an end that's partial negative. Very important that you know it's partial, not full, partial negative. And you have an end that's partial positive. Another example would be water. Okay, so water, nonmetals, so they're going to have sharing, covalent bonds. This is the structure of water that we'll talk about later on in the course. But again, you see this bond here. This is not a 50-50 equal sharing bond. In fact, the oxygen is pulling the electron density more towards itself, not only on this end of the molecule, but also on the other end of the molecule as well. So what makes water remarkable, as well as formaldehyde, is that within the water molecule, you have a partial negative charge. The other ends are going to be partial positive charge. This Greek symbol delta just means partial. And what we see here are what are known as polar molecules. The reason why you have polar molecules is that oxygen has a larger electronegativity. You can see the trend here in the periodic table. Larger electronegativity and more of an electron pull, and that makes the molecule not neutral, but partial negative on one side and partial positive on the other side. Let me give you another example. Okay, again, we're really focusing on covalent molecules here. Let's say I have C with 3 H's and an F. Okay, notice the single bond, single bond, single bond, and single bond here. Covalent molecule. Fluorine, again, in this electronegative region of the periodic table, very, very electron affinity, very, very high electron affinity. So that fluorine is going to pull at this bond. So one end of the molecule will be partial negative. The other end of the molecule will be partial positive. So that is the trend with regards to electronegativity. When you have a chemical bond, a covalent bond, whether it's single or a double bond or a triple bond, if you see an oxygen, nitrogen, phosphorus, fluorine, and the halogens, it's going to pull, and it's not a 50-50 equal sharing bond. Just more electron affinity in this end of the periodic table, but this is really an issue, the nonmetals, because remember, the metals tend to push away electrons. The nonmetals, particularly here, tend to push electrons towards itself. These guys tend to pull electrons away from itself. This is a very important concept. What we've shown here are 3 examples of polar molecules. It's polar only because one atom in the molecule is sucking more of that electron density, sucking more of that negative charge more towards itself. And the trend is that the electronegativity or electron affinity increases across a period, and it decreases down a group of the periodic table. Again, we're really focusing on the nonmetal side of the periodic table, because nonmetals are the ones that really are going to pull, like a vacuum cleaner, electron density towards itself.